Welcome to our FAULHABER Drive Time. In this video, I want to check the influence of different encoder systems to the control loop performance. And to do so, I got different motors. I usually would use the 22mm ones, where we do have the linear Hall or a magnetic incremental encoder or an optical incremental encoder or the Absolut encoder, again magnetic, either single turn or multi-turn. But for your benefit, I don't use the small ones, but I'm going to use the big ones here, 32mm diameter, because then it's easier to watch them in the setup here. But reconfiguration here, once again, hooking up all these motors takes some time, so we are going to use some time lapse and cuts in this video to have you concentrating only on the main aspects here. In the end, we will see me using the drive configuration window and the tuning window, and then in the end I will summarize the results with a single slide. So let's start this. Let me grab my PC and we can start here. So here with the first one, it's the one having the linear Hall sensors here. Okay, I have to connect it to the motion controller. Only two connectors in that case, and can start configuring. And first one, of course, select the motor, and that's still the one that I used in the last videos. So here, that's the bigger one, 3268, and it's a 24-volt execution, and it's having linear Hall sensors as the one in the first videos had. And as I only have the linear ones, these are going to be used for all the loops. Once again, the check for the supply voltage with the threshold, and then transfer the configuration. And for the linear Halls, there's always the option to adjust the Hall sensor signals, so to teach in the Hall sensor signals to the controller here, and this takes a few moments and is better done without any load connected to the motor. The disk doesn't harm here, but no friction or something like this. And that's a one-time exercise that we have to do to more or less pair the motor and this controller. And then we are done here. I could save the parameters, but I don't have to. And then I'm using the configure controller tool to identify the inertia. I'm doing this once only here in this video, because of course it's always the same motor, same disk, so I can use this value for the next ones too. Use the startup method here. It's a pretty small disk, at least compared to this motor here. Okay, check the result. Yeah, a factor of roughly a little more than the idling motor here. And again, transfer the configuration, and that's an important step because now all the control loop parameters are preset for the now identified inertia, and of course for the motors that I selected here. Transfer configuration, and I'm done here. And again, I don't need to change, save it, and then use the controller tuning, and always the same steps here. So here is the comparison between the four encoder systems on a single page. First for the step response, and the next one is going to be for the position. It's always been a step to 1000 RPM, and the yellow line would be the demand speed, whereas the green one is the current and the blue one is the actual speed. And we can see a very similar behavior for all of them, but obviously for the magnetic ones, that's the left column here. On top it's the magnetic incremental, and on bottom it's the magnetic absolute. This is a behavior which is very similar when we compare these small oscillations here on the right side. it's the linear halls on top and the optical on the bottom here. And when we compare the oscillations in the actual speed, the blue line here and the blue line down here, we can see that for a constant speed operation, the optical encoder is superior. So it's got the lowest oscillations in this speed loop because it's got the highest precision, lowest error that we have in these encoders. When we now compare the reaction in a single turn of the motor, there is a blue signal and a yellow signal, which are the actual value of the position and the demand position. And in all of the four pictures here, we have a very perfect following of these two lines. The green one is the triangular speed here during this move, and then the remaining one would be the current here. And when we compare them, it's very similar. So for precision loop, there isn't much difference between the linear Hall and even the optical one, at least while we still use the standard parameters for these motors. The optical does have its benefits because, as I explained, I can increase the gains here and would have better compensation of the disturbance. A table to compare the results. These are the four sensor signals that I used here, and then this is the response to a speed step. It's first the rise time, which is the time from 0 speed to first being into the corridor of the target speed, and the settling time, which is the time that we need from starting at 0 to finally be in the target corridor. And as you can see, the optical one is pretty good in that case here, whereas the other ones take some time due to the ringing that we've seen. For the time per single turn, these ones are pretty similar here. It's the same resolution and similar precision of these encoders here, whereas the optical one with the default settings would use the same time, but it can be tuned due to the higher gain for the parameters and can be pretty fast in such a case, and that's due to the better precision of this encoder. Of course, in that case, gains have been increased and the braking chopper has been used. So far about the influence of different encoder systems in a control loop. If you got any questions about the encoders or the motor controls itself, don't hesitate to contact our local sales team or contact our MC support team. And of course, feel free to leave a comment below the video here. Thanks for watching, and check back with our channel, and bye.